Alright, in today's lesson, we're finally getting to graphing polynomials. The last couple of days we've been focusing on the characteristics and pretty much what graphs would look like based on the characteristics and the polynomial function itself. That was where the matchmaker came into play yesterday that you were supposed to be working on. Now, the standards that are addressed today would be basically just graphing simple polynomial functions, and then understanding the effects of the graph of a polynomial function using the degree and leading coefficient and the multiplicity of the zeros. Those are all key factors, along with the end behavior when it comes to graphing. Now, you have your notes. We're going to work on a few guided notes to start with, and then we will work into graphing a couple of polynomial functions. Then I'll leave the rest of them for you to work on by yourself. Now, the first step for graphing polynomial functions is to find the x and y intercepts. So if you're thinking about a list of things to do, and you're going, all right, step by step, how am I going to graph these polynomial functions, especially to start with, the first thing you want to do is find the x and y intercepts. The second thing, under these x and y intercepts, you can find the x-intercepts by finding the zeros of the function. In the last 3 weeks, we focused on finding the zeros of the function in a different unit, and we found them through factoring, factor by grouping, greatest common factor, and of course when we got into really large polynomials, we used the rational root theorem and synthetic division. So let's keep those in mind when we're trying to find the zeros of our function. The second thing is finding the y-intercept. It's very simple. Evaluating the function for x equals 0. Yes, that's all it sounds like. You just plug in 0 for x, and whatever's at the end is your y-intercept. Thinking back to linear functions, where it was y equals mx plus b, yeah, that b at the very end, that was the y-intercept. Same thing with polynomial functions. Alright, the second thing you must do, make a table and select values of x that are between the function's zeros. So once you find all the zeros, you can see them, find some place in the middle of them, and you will evaluate your function at that point so that you can see a relative max and a relative min on your graph, much like what we talked about on the first day of this unit. The third thing is determine the function's symmetry. Alright? Is the function even? Is it going to be odd? We talked about this on the first day. A function is even if all the exponents are even, and a function is odd if all the exponents are odd. If none of them, if it's not all even and it's not all odd, then it's neither. But symmetry plays an important role when it comes to graphing. Because if I know it's supposed to be symmetric across the y-axis and it doesn't look that way, I must have graphed something incorrectly, or I evaluated one of my zeros incorrectly. Alright, and the last thing is to determine the function's end behavior. And we know end behavior. End behavior has to do with the leading coefficient and the degree of the polynomial. We talked about that a little bit on the first day. And then with the matchmaker yesterday, you were able to line up those end behaviors with the function based on the graph. I admit it's easier to look at it graphically and see the end behavior than it is, in most cases, to look at the polynomial. But I want us to be able to get into the habit of going back and forth, one way to another. In the first example, we have to find the roots of the function first, or the zeros. And the reason it's called these zeros is because we need to set f of x equal to 0. So I have 0 equals 2x cubed minus 5x squared minus 2x plus 5. On your paper, you probably have more room to work than I do up here on the board. That's fine. You don't need to write yours in the graph func area. You can write it on a piece of paper. Right away, you notice that this is factor by grouping. Factoring out the x squared, I'm left with 2x minus 5. In the second group, I'm going to factor out a negative 1. That leaves me with 2x minus 5, and I have my two groups. X squared minus 1 times 2x minus 5. Set each of these equal to 0. X squared minus 1 equals 0. 2x minus 5 equals 0. And from here, using your basic algebra, you should be able to tell that two of the zeros are positive and negative 1, and the other one is 5/2. Alright, now we must find the y-intercept in order to help us graph. The y-intercept is quite easy. On the first one I'll show you, we said we needed to set x equal to 0. That's 2 times 0 cubed minus 5 minus 5 times 0 squared minus 2 times 0 plus 5. All of these become 0, and our y-intercept ends up being 5. Now, I have these things. I have my zeros, and I have my roots. I have my roots and I have my y-intercept. Now I'm ready to graph. I would go ahead and pick these points, and then, like I said, we'll go back and find the table and pick the points in between. Alright, so one of our zeros is at negative 1, one of them is at 1, and one of them is at 5/2. Now, 5/2 is the same thing as 2.5. So there it is. We also have a y-intercept at 0,5. So, I've put in all my points. The next thing we have to do is, you can physically make a table on your paper, or you can just think of one in your brain just a little bit. But whatever you need to do, you need to find points in between the zeros that allow you to see where our maximums and minimums are going to be. Because as you know from looking at the matchmaker and some of our other functions, our graphs are big curves that dip and move and continue in that format. Well, we came out with lucky because in between negative 1 and 1, we have a maximum. We can see a place where the function changes. Now we need to find a place in between 1 and 5/2. I would recommend that we just use a whole number. Don't get involved in, well, the exact places in between 1 and 2 and it needs to be a fraction. Let's just pick the point 2. We know it's going to be down here. Pick the point 2 and use synthetic division to find your answer. 2, negative 5, negative 2, and 5. Bring down your 2, that's 4. 2 times negative 1 is negative 2. That's negative 4. That gives you negative 8. And our answer is negative 3. Alright, so at the point 2, negative 3, we are down here. Now I realize that this isn't exact, but it is a kind of a rough area of where the function will be turning back around. It's not going to go way down here and then dip back up in this short of amount of space. So we can be quite confident in that. Alright, now the third thing we want to do is determine whether there's symmetry about this function or not. Well, considering it's an odd and then an even, automatically there is no symmetry. So we don't need to worry about whether it's going to be symmetric about the y-axis or symmetric about the origin. From here, let's talk about the end behavior. If I'm thinking about the end behavior, I need to focus on the leading coefficient and the exponent, the degree. Well, the leading coefficient is positive, and the degree is odd. So therefore, as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. So much like linear functions, this function is going to start down in the third quadrant, coming from this negative infinity area, coming up, and it's going to turn and then head back up in the negative, the positive infinity area as x approaches positive infinity. So it's going to look something like this. We're going to come here, make our change, go back down, and then go back up. And now we have roughly sketched a polynomial function. All right, let's look at another example. We've moved on to number 3. Now number 3 is not going to work out so easily. As you can see, this is a cubic, but it will not work by factor by grouping. We need to think about using the rational root theorem. All right, so some of our possible zeros would include positive and negative 1, 2, 4, and 8. So any one of these might work, and none of them might work. We don't know. We just have to work through them and figure them out. I'm going to start with negative 1, using my synthetic division. 1, negative 3, negative 6, and 8. Remember, if I get 0 at the end, then I know that this is a 0 for the function. Bring down my 1, negative 4, that becomes 4, and already I can tell this is not going to work. So, I will start again, and I will use 1. That's 1, negative 2, that gives me a negative 8 and negative 8. Yay! We found one of our zeros. Wasn't that hard this time, and luckily 1 was the 0 that we could start with. So I know that that one is going to work. If you remember about synthetic division, you know that this breaks down into x squared minus 2x minus 8. Because it's a quadratic, try to see if it factors first. If it doesn't, use the quadratic formula. This will factor x minus 4, x plus 2. From here, set each one equal to 0. And you can see right away that our other zeros are 4 and negative 2. All right, so let's put those on here. 4, negative 2. If you remember from the last function, the other thing we have to do is find the y-intercept. Plug in 0 for each of these, and whatever comes out at the end, that will be your y-intercept. We can clearly see that it is positive 8. And now we are ready to pick some points in between our graphs and our zeros and graph our function. Alright, for the points in between negative 2 and 1, I already have 8, but I can go with negative 1 just to kind of see what else I'm going to be dealing with here, to see how high my function might be going. And over here, I'm just going to use 2. So let's start with the negative 1, using the synthetic division. Alright, we end up with 10 when x is negative 1. Let's try 2. All right, when x is 2, y is going to be negative 8. All right, so this is a pretty good number of points that we have for our function. The next thing we need to do is look and see if we have any symmetry involved. I've got a cube and then squared. That automatically voids out any symmetry because it's not odd and it's not even. All right, let's go to in behavior. My leading coefficient is positive. My exponent is odd. So, like the last one, as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y approaches positive infinity. So once again, I'm going to be starting down in this area with my arrow and ending up here once I've gone through all of my roots. Alright, there is a rough sketch of what our graph would look like. Alright, we went ahead and skipped ahead to number 5. I wanted to show you number 5, then I'm going to leave you to do the rest of the examples as homework or classwork so that you can have some practice working on them by yourselves and determining what types of things you can come up with. In number 5, we can clearly see that it is going to be factored by grouping. I will factor out the x squared, leaving me with x minus 2, and then factor out the negative 4, leaving me with x minus 2. Continuing on with the steps, I realize that I have x minus 4, x squared minus 4 equals 0, and x minus 2 equals 0. That will yield positive and negative 2, and then a 2 for my answers. What I want you to pay close attention to here is that I have positive 2 showing up twice. So, when I put in negative 2 as one of my zeros, and I will also have positive 2 for one of my zeros. Now, multiplicity. We've talked a little bit about multiplicity in the past where a 0 shows up twice and everybody's fine writing it and everything. But graphically, we haven't discussed what happens when you have a multiplicity. Well, let's keep going and we'll get to that point in just a minute. This would be our y-intercept. We need to pick some points in between our zeros. The only two that we have are negative 2 and 2. And I'm perfectly fine with leaving 8 as the y-intercept, and then we'll discuss what happens from there. We'll talk about the in behavior and symmetry. There is no symmetry because you don't have just odd function exponents or even exponents. So it's going to be neither. The in behavior, as we've talked about before, in this case is y approaches negative infinity as x approaches negative infinity, and y approaches positive infinity as x approaches positive infinity. Now this is going to be kind of weird to think about because look at this graph. We've only got 2 places for zeros. Now don't keep in mind multiplicity of 2 here, positive 2, because my zeros are negative 2, 2, and 2. So something has to happen where I start down here and end up there. So here we go. I'm coming from this direction. I know I'm going to change directions when I hit the y-intercept. And then when I come down here, because this is a multiplicity of 2, I'm going to bounce off of the x-axis and go right back up in the positive direction. So, as you can see, when we have a multiplicity of even numbers, like there's 2 multiplicity of 2, or maybe it's a multiplicity of 4, or a multiplicity of 12, it's going to bounce off of the x-axis and go back in the direction that it came from. This is how our in behavior stays in its rational form in the way it should be. Alright, that concludes our segment on graphing polynomial functions for today. I hope that you follow the steps. Remember that graphing rational functions or polynomial function, excuse me, is not that difficult. Just remember to find the zeros. Use your characteristics that you think are important, like using the end behavior and the odd and even symmetry of a function. Thank you.